So now that we've introduced the term or variable enthalpy, again, that's heat flow under constant pressure, we need to talk about a few other variables that are helpful or can be utilized to calculate changes in enthalpy. But I first want to define what the standard state of an element is. And the standard state is the most stable physical form of an element under standard conditions, which are assumed to be, or defined to be, 1 atmosphere and some specified temperature. And in this case, it's assumed to be room temperature, or 25 degrees Celsius. So now that we understand standard state, we can talk about standard enthalpy of formation. And this basically is an arbitrary scale that was established in order to be used as a reference point for all enthalpy expressions. So the standard enthalpy of formation, whoops, just trying to underline that, is abbreviated by this, delta H, superscript naught, subscript F for formation. So this indicates we're talking about standard, the superscript. So the standard enthalpy of formation is the heat change that results when 1 mole of a compound in its standard state is formed from its constituent elements in their standard states at a pressure of 1 atmosphere. So let's look at some delta H's of formation, and if that element or compound is in its most stable physical state or standard state, it will have a heat of formation of 0. Here's an example of molecular oxygen, which is O2 as its most stable physical state, has a delta H of formation of 0, compared to ozone, which has a positive heat of formation. So that is an endothermic process. Delta H of formation for carbon in the form of graphite is 0. It's its most stable physical state, compared to another, or an allotrope, which we'll discuss that term later, of carbon is diamond, and it too has a positive delta H of formation. This is a table from your text, and you'll note that where you see all the zeros and you look at the elements involved there, most of the metals, of course, are solids. The halogen Cl2, where we have F2, H2 is not a halogen, but it's one of those 7 elements that exist in the molecular state, I2, so forth. All 0 heats of formation because they're in their most stable physical state. So what do we use these for? We can use them to determine standard enthalpies of a reaction, assuming it's carried out at 1 atmosphere, standard or constant pressure. And we can use these to predict the heats of the heats formation, to predict the heats of reaction by determining the difference between the standard heats of formation between reactants and products in a balanced equation. So this is a direct approach to calculating the delta H of a reaction, in this case the standard enthalpy of a reaction, from the heats of formation of the reactants in the products. So here we have a generic chemical equation. The lowercase letters indicate the coefficients, and of course the uppercase letters represent the elements or compounds. And the setup of these to calculate the standard heat of a reaction using heats of formation is multiplying the standard heat of formation of each component in the equation by its coefficient. And you'll notice that C and D are added first, and in the first of this equation, and we subtract from that the sum of the standard heats of formation of A and B. So this is the sum of the standard heats of formation of the products that are multiplied by their coefficients, if it's greater than 1, and subtracting from that the sum of the heats of formation of the reactants having been multiplied by their coefficients. So that's a direct method. There's an indirect method, which we call Hess's law. And this is utilized when reactants are converted to products. The change in enthalpy is the same whether reaction takes place in one step or in a series of steps. And Hess's law is applied to chemical reactions that, when producing products, do not occur in only one step. Some reactions have to go through several steps in order to get to their products, and we'll take a look at how we can handle those types of problems. Remember, enthalpy is a state function. It doesn't matter how you get there, only where you start and you end. So before we move on and do some problems or example problems of directly calculating the standard heat of a reaction using the heats of formation, or stepwise using Hess's law application, I want to talk about something that's called a formation equation. So the definition of the standard enthalpy of formation, or delta H of formation, we know is the heat change that results when 1 mole of a compound is formed. In its standard state, from its constituent elements in their standard states. Okay, so I'm going to write an equation here. N2 gas plus 3H2, 2 gas, gives 2 NH3. Gaseous. And this is a thermochemical equation. The standard heat of this reaction is negative 92.2 kilojoules. Okay? So while this is a thermochemical equation, it is not a formation equation. So it's not, this equals the standard heat of the reaction, but it doesn't equal this. Okay? In order for us to find the standard heat of formation, we can only produce 1 mole of product. So the formation equation is 1/2 N2 plus 3/2 H2 to give us 1 mole of ammonia. And these were all still gaseous, sorry. And so the heat of formation, we now need to divide the standard enthalpy of the reaction by 2, because that was for production of 2 moles of ammonia. So the standard heat of formation for ammonia is a negative 46.1 kilojoules. Okay, so this is the only case where we allow fractions as coefficients. All right, so now we're going to take a look first at the direct method of calculating the standard enthalpy of a reaction using the heats of formation. But we're going to take a look at this graph first. So, of course, this is enthalpy, and we have graphite plus O2 gaseous. And this is written in a stepwise manner, forms carbon monoxide and 1/2 O2 gaseous. And we can add these reactions together and come up with CO2 gas. So here's the summary of that. So graphite, graphite plus 1/2 O2 gives us carbon monoxide. Carbon monoxide by another 1/2 O2 gives us CO2. If we add those together, we come up with this overall reaction, with this being the product. Okay? And let's see. I will do that on the next page. So this is the enthalpy of formation of CO2. We are making 1 mole of CO2. So let's look at the direct calculation in which we would use the standard heats of formation. So we're going to use standard heats of formation to determine the standard heat of reaction which in this case, because we're producing 1 mole, would still be the heat of formation as well, for 1 mole of CO2. And carbon in the form of graphite plus O2 gaseous gives us CO2 gaseous. And we can look up in a table that the standard heat of reaction is negative 393.5 kilojoules. But we're going to calculate it first using the direct method, which is the heats of formation. In which the standard heat of this reaction equals, excuse me, the standard heat of formation of CO2 there's only one product, minus the standard heat of formation of carbon plus the standard heat of formation of O2. Oops, O2. Okay, so again, we can look up those standard heats of formation in a table in the appendix of your textbook, and you will find that the standard heat of formation of carbon dioxide is negative 393.2 kilojoules. And both carbon and oxygen, molecular oxygen, are in their most stable physical states, so their standard heats of formation are 0. So delta H, or the standard heat of this reaction, equals negative 393.2 kilojoules. And this is per mole. 1 mole. So as I mentioned, we use Hess's law for compounds that can't be directly synthesized from their elements. So we can determine delta heats of formation using Hess's law when the reactants are converted to products and the enthalpy change is the same, whether the reaction takes place in one or more steps. Okay, so again, remember, enthalpy is a state function. So we can apply Hess's law to CO2 formation. I'm not sure why this, there we go. So this is going to be an indirect approach because it's more than one step. Hess's law. And in this, I'm just going to write those reactions. We know that carbon in the form of graphite is required. We know that O2 is required. And here we've just looked up the standard heats of formation, in this case, for carbon monoxide. Or standard enthalpy of the reaction. This is negative 110.5, and that's in kilojoules. And then we can react carbon monoxide with another half mole of oxygen. And so again, these are heats of these are formation equations. In this case, they aren't always. And this is negative 283.5 kilojoules. Now I can add these together and cancel anything that doesn't appear in the overall equation. And carbon monoxide appears on opposite sides of the arrow in two different equations, so I can cancel that. And now I can just sum the remaining components to come up with the overall equation. And sum those standard heats of reaction or standard heats of formation, and I get negative 393.5 kilojoules. And this is per mole. Okay, so you get the same standard heat of reaction whether you use the direct approach or the indirect approach. Okay, so let's try another one of these. We're going to look at the synthesis of H2 gas or molecular hydrogen. And this is synthesized from methane and steam or water vapor. And this process is used in the steel industry to move impurities from molten iron, and in the chemical industry to make hydrogen containing compounds like fertilizers and so forth. So there are two steps in this process. And the first is the reaction of methane with gaseous water or steam. And this produces carbon monoxide and 3 moles of H2 gas. And the standard heat of this particular reaction is a positive 206, and this is kilojoules. Again, second step is the carbon monoxide from the first reaction also reacts with gaseous water and produces CO2 gas and another mole of H2 gas. And the standard heat of this reaction is a negative 41 kilojoules. I'm going to add these two reactions together after I cancel components that appear on different sides of the arrows, and that is carbon monoxide. So I can sum these now, and I get CH4 plus 2 moles of gaseous water, giving us 1 mole of CO2 and 4 moles of H2 gas. I also need to sum then my standard heats of the reaction. So for the overall reaction, the standard heat of reaction is a positive 165 kilojoules. So that was an application of Hess's law. So let's talk a little bit more about Hess's law problems and the rules. I don't know why I pen. Rules for manipulating thermochemical equations. Get that I in there. Okay. Number 1, and we haven't seen this yet, but if we need to reverse an equation, we must also reverse the sign of delta H. So if an equation is reversed, reverse the sign of delta H. And we have seen this. If there are identical formulas, on opposite sides of the equation. And I'm just going to say arrows. We cancel them. And lastly, if coefficients in an equation are multiplied or divided, delta H must be multiplied or divided as well. So it needs to be treated the same way that the coefficients in the equation have been treated. Okay, can we have an example of that? Yes. Oops, no, I thought I had another page here. Okay, we'll come back to that, but I think this problem will give us, it will give us some of the rules, or you'll be able to see some of what we just talked about. So this is the format of a typical Hess's law problem, where you're given a set of equations with their associated standard heats of reactions, and ask you to use them to come up with a standard enthalpy of formation for, in this case, CS2 liquid. So that means you need to manipulate these equations to come up with the standard heat of formation for the formation of that liquid or that product. So first thing that should be done is write the enthalpy of formation equation for CS2. So remember, that is the compound, or in this, well, it's a compound, the compound's formation from its constituent elements in their most stable physical state. So looking at the set of reactions we've been given, we see that the first reaction, C graphite, so there's the carbon, and we also see S rhombic. And those are the two elements that have to react in order to form CS2. So those thermochemical equations are in the correct orientation because we want both those elements on the reactant side. But what do we want on the product side? CS2. So this is our formation equation for CS2 liquid. C graphite plus 2 S rhombic. We have a 2 in the product, so we have to have 2 moles of S here. So now we need to manipulate these equations to give us this overall equation once we add them together. So we are going to do just that. Oops. So here's the first equation as given up here. We don't need to change anything. It's in the correct orientation. We don't have to multiply anything, no manipulation. Now we get to the sulfur component. And we need 2 moles of sulfur. This equation only gives us 1 mole. So that means we have to multiply every coefficient by 2 in the equation, and we also have to multiply delta H of the standard heat of formation for the reaction by 2 as well. Oops. The third equation is the equation that contains our product, but in the original reaction we were given, it isn't in the correct orientation for making CS2. So we have to flip this. So this gets flipped. This one got multiplied by 2. All the coefficients. And so here we see this has been flipped, and when this flips, that negative 1072 becomes a positive 1072. Now we can add them together. We can cancel all the components that don't appear in our, I'm going to call this target equation. There's no CO2 there, so we can cancel, I started with oxygen, sorry. There's no O2 there either. And we have 3 moles of O2 on the left side of these equations, and we also have 3 moles on the right. So those can be canceled. And now we can look at carbon dioxide. There's 1 mole on the left and 1 mole on the right. And one more component that doesn't belong there is SO2. So those can be canceled as well. And now we can add those together. We get our target equation. And now we also sum our delta H's. So the standard heat of formation reaction, or the standard heat of reaction, is a positive 86.3 kilojoules. This would be an endothermic reaction, because it's positive, right? Now we're going to take a look at heat of solution, or the dissolving process. And the example here is using sodium chloride. But we're going to apply Hess's law. And basically, what we're going to do using Hess's law is related to the Born-Haber cycle. And you can review that in your text if you wish. But your text asks you to imagine this dissolving process in 2 steps, where step 1, the sodium ions and the chloride ions in the solid state are converted to gaseous ions. And the energy associated with that is called lattice energy. And it's represented by a capital U. And this is the energy required to separate 1 mole of solid ionic compounds, or a solid ionic compound, into gaseous ions. And these have also been determined experimentally. So the lattice energy or U, for sodium chloride is 788 kilojoules per mole. And the second step of this process is heat of hydration. So these gaseous ions react with water to make aqueous ions. And the delta heat of hydration has also been determined, and that is a negative, oh wait, is it? Yeah, negative 784. So if you look at this, the heat of solution, which we can determine using calorimetry, has been found to be 4 kilojoules per mole. And if we use Hess's law and to calculate the heat of solution, we will also come up with 4 kilojoules per mole. And maybe I think I did have another slide here. If I didn't, I'm in trouble. But I think I wanted to cover this. But the delta H of solution then is going to be the sum of step 1 and step 2. Oh, well, if I don't, it is here. We have 4 kilojoules per mole. Oh, okay, good. So let's actually just talk through that. And so, again, we're going to apply Hess's law and heat of solution here. And so our delta H of solution is going to equal lattice energy plus the heat of hydration. And that's the energy or enthalpy change associated with that solvation for negative and positive cations. It applies to both. And so I do want to point out, though, that the delta H of solution may be positive or negative. It depends upon the nature of the anions and cations involved too. So it's not something you can predict. You need to calculate the delta H for that. So we have sodium chloride solid, and that is in step 1. Those become gaseous ions. And our lattice energy, 788 kilojoules, and this is per mole. And then those gaseous ions will be hydrated. And that means they're surrounded by water, essentially. And so we have an aqueous state now. I don't know that I left much room. And this is the delta H of hydration, which was negative 784. So now we can sum these. Sodium gaseous ions cancel, gaseous chloride ions cancel, and we get NaCl solid. Do show that water here. We have sodium, aqueous, and sodium ion, and chloride ion, aqueous. And the delta H of that solution then is 4 kilojoules per mole. Okay, I might be able to work in a few extra Hess's law problems. You should become pretty familiar with how to manipulate those equations. So get to practicing some of those.